Morning, Gopal.
Hi, Lokant. Good to see you.
Good morning,
I
Gopal.
understand
Good to
over
see you.
1400 registrations, huh?
Oh, that's excellent. Uh,
I wonder if they can hear me. Hello? Hello? Hello?
Morning, Mr. Stuart
Morning.
Parker. Good morning.
Yeah, morning.
Good morning.
Thanks, yeah.
So you can see and hear me well?
Yeah.
Yes, very well.
Okay, fantastic. Great. So you start in a few minutes.
Yes, we will start in a few minutes. Yeah.
Okay, fantastic.
Hi sir, host this side. We are ready to go live.
Ready to go live.
Want to start now? Can start.
We can start secretary.
Secretary nahi hai abhi, but he will. His talk is later, right? So
Yeah.
you want to call him once just to see. Good morning, ladies and gentlemen, to this glorious day. I, Hemojit, on behalf of the organizing committee, warmly welcome you on this 5th International Conference on Emerging Electronics, ICEE-2020. To begin this inaugural function, may I request Professor Neeraj Khare sir, General Chair ICEE-2020, to give the welcome address. Over to you, sir.
Good morning, Sri Ajay Swani, Secretary Mighty and Chief Guest of today's function, Professor Ram Gopal Rao, Director IT Delhi, Professor Ashok Ganguly, Deputy Director Strategy and Planning, Professor Naukan Bhatt, Head Sense ISC Bangalore, Professor Rajen Singh, Technical Chair of the conference, Professor Bhaskar Mitra, Tutorial Chair of the conference, invited speakers, delegates of the conference. I'm very happy to welcome you all on this International Conference on Emerging Electronic. I also welcome to the viewers who have joined this inaugural function through IT Delhi YouTube channel. The present International Conference on Emerging Electronics is the 5th international event in a series which was held earlier at IIT Bombay in 2012 and 2016 and at IIC Bangalore in 2014 and 2018. The focus of the conference is on advancement of emerging electronics, starting from materials to device and integration to system. After the last conference, which was held in IIC Bangalore in 2018, it was decided to hold this conference in IIT Delhi like a usual offline conference. We actually started preparing for that. But due to the COVID scenario, we have decided to hold this conference as a virtual conference. Seeing the scope of this conference, I'm happy to inform you that many international and national world-renowned leaders have accepted to give talk in this conference. We have more than 150 invited speakers. There will be 8 parallel sessions. I think Professor Rajen Singh will describe more about the technical program of the conference, and Professor Bhaskar will talk about this tutorial program of this conference, which held yesterday very successfully. And seeing the scope of the conference, in spite of the COVID scenario, we have very good participation. 1,400 participants have going to join this conference. And apart from that, we are also going to stream the keynote address and plenary talks and evening talks of this conference in the IIT Delhi YouTube channel, so that many students and the faculty can watch this program. So this being an online conference, we will not have the advantage of meeting in person, but all these symposia conveners and local organizing committee members have done a lot of hard work to make this conference technically stimulating. We hope that the conference will provide good opportunity for researchers to listen to the world-renowned leaders and also to interact them online. Thank you very much.
Thank you, sir. Now I would like to request Professor Ram Gopal Rao, sir.
Yeah. Welcome to IIT Delhi. And because of COVID, we are not able to have all of you person. But no. But otherwise, I think the conference has attracted a large number of participants from all over the world. As Professor Neeraj Khare mentioned, over 1,400 people have registered for the conference, which is a good sign. I think usually during the normal times, the conference used to attract 500 to 600 people. And I think the virtual event is now at least twice that. But I think probably herein lies the way forward for the conference. I think a hybrid kind of an approach is what we need to follow in the future. While there can be in-person sessions, because after all, conferences are meant for networking purposes too. So while there can be an in-person kind of presence, but I think we should also now start streaming all of our conferences online and have the virtual registrations. So I think we will now do it this way, hopefully starting from the next event. This is also the IIT Delhi's Diamond Jubilee year. So we are also in a way organizing this event as part of our Diamond Jubilee celebrations. IIT Delhi is celebrating its 60th year that way, and I think this is also a momentous occasion for us. Mr. Ajay Sani will also talk about the surge in electronics manufacturing in India. There is a lot happening in India when it comes to manufacturing. Of course, all of it is currently limited to assembly level of manufacturing, but even the device and component level manufacturing, there are a lot of initiatives right now. I hope something on the device and component level also will happen in the near future. So, but academia in India, when it comes to emerging electronics, semiconductor devices, is going great guns. Thanks to again Ministry of Electronics and Information Technology, Department of Science and Technology, DRDO and various other agencies, all our premier institutions now have excellent nano research facilities. We can fabricate now 10 nanometer, 20 nanometer kind of devices in our academic institutions, and that we can do at least in 6 or 7 leading institutions in the country. And these institutions are also now partnering with other institutions so that others who cannot maintain such facilities or afford the high costs involved in setting them up can also access these facilities. We have the Indian Nano Electronics Users Program, which is again supported by Ministry of Electronics and Information Technology. Thousands of people now have access to these facilities in the country. That is also reflecting in the quality of research that is done in the country. Papers appearing in leading journals all over. Every IEEE transactions on electron devices you see today, you will find a few papers from India. I think things are looking good, and also startups are emerging out of these nano research facilities. While we don't have any manufacturing component device level manufacturing foundries in the country, but there are many startups now which are in the sensor space. So there is a lot of interesting work that is happening through these startups, which is reaching people. I think things are on track, and I am confident this conference will set a new trend for the future ICEs, the future international conferences in emerging electronics, and also for other conferences. And I'm very happy, and I would also like to congratulate my entire team here as well as in various other institutions in making this a very successful event. Thank you very much.
Thank you, sir, for sharing your thoughts. Now I would like to request Professor Navakanta Bhatt, IIC Bangalore, who has joined us online, to give a brief background of ICE. Over to you, sir.
Thank you very much. Good morning to all of you, specifically Sri Ajay Saniji, Secretary Mighty, and Professor Stuart Parkin, who is going to give a keynote talk later. So I thought I'll take a few minutes to give you a brief background of how ICE started. At the turn of the century, there were two very important developments in the country. One was from the IEEE perspective. As you know, IEEE is the largest professional body in the world. The IEEE Electron Device Society was growing in the Asian region and in particular in India at a very, very rapid pace with several chapters coming up. And we started having yearly discussions among the Southeast Asian chapters to start thinking about how do we really, provide value to IEEE members. At the same time, there was another very important national initiative driven by Ministry of Electronics, thanks to the foresight of the officers at MIT, which launched the National Nanoelectronics Initiative and established a Nanoelectronics Center of Excellence at IIT Bombay and IISc Bangalore. This was back in 2005. And these two different vectors sort of came together and amalgamated, and we thought maybe this is a great idea to provide a forum so that all the research that happens in these two centers and also through the INUP program that Ram Gopal mentioned, there will be a platform for researchers to come together. And this discussion started, thanks to Professor Renuka Jindal from US, who was then EDS president, and M.K. Radhakrishnan and Ram Gopal, myself, Rudra Pratap, Professor Vasi, all of us brainstormed quite a bit. And we decided to start the biennial conference between IIT Bombay and IISc Bangalore called International Conference in Emerging Electronics, technically co-sponsored by IEEE Electron Device Society. That's a very important thing because, that gives the required visibility to the conference, right? So, as Professor Neeraj Khare mentioned, 2012, it happened in IIT Bombay. The first conference was about 200 people, registrants. 14 was in IISc Bangalore. The registration started going up year on year. 16 was again in IIT Bombay, and 2018 was in IISc Bangalore. That is when we had close to 600 registrants. One of the largest IEEE EDS conferences anywhere in the world, right? Probably next to IDM, right? So that is the stature this conference has reached. And at the same time, there was another very important initiative from MIT to expand the network of IISc Bangalore and IIT Bombay through a national and Madras into this national initiative. So that is when we decided, and we took in 2018 that the next conference should happen in IIT Delhi, and perhaps alternately years it can come back to Bangalore and go to other venues, right? So that is how we are at this conference now. Unfortunately, COVID has really affected the way it would have happened in person, but there is still a silver lining, as Professor Ram Gopal mentioned. We have record number of registrants today, and this is a great sign for this conference. And also the way things are shaping up in India, in electronics and nanoelectronics and related areas, and also the fact that it is being recognized by the world body, which is IEEE and IEEE Electron Device Society. Thank you again. I hope all of you will have a great time in the next few days.
Thank you, sir, for giving us the background of ICEE. Now I would like to request Professor Rajendra Singh, sir, Technical Chair ICEE 2020, to give us the insights of technical program for ICEE 2020.
Thank you. So, respected Chief Guest, Mr. Ajay Sahni, Secretary Mighty, Professor V. Ram Gopal Rao, Director IIT Delhi, Professor Ashok Ganguly, Deputy Director IIT Delhi, Professor Neeraj Khare, Professor Bhaskar Mitra, and Professor Navkant Bhatt from ICEE Bangalore. Our keynote speaker, Professor Stuart Parkin, our esteemed speakers, dear participants and attendees. Good morning to all of you. It is my honor and pleasure to welcome you all to the inaugural session of ICEE 2020 at IIT Delhi. as a technical chair of the conference, I would like to give a summary of the technical program for this conference. So this conference is basically spanning over 3 days, from 26th to 28th November, and was preceded by one-day tutorial session on 25th November that successfully took place yesterday. So in this conference, we have 11 technical symposia, and the themes of these symposia are ranging from 2D materials and devices, wide bandgap semiconductors, then we have device modeling and simulation, photonics and plasmonics, photovoltaics, biosensors and bioelectronics, spintronics, RF and terahertz devices, and emerging logic, memories, and neuromorphic devices. So all of these topics are contemporary areas of research having wide-ranging applications in electronics. And in these technologically important areas of research and development, we will listen to many interesting talks delivered by eminent speakers and researchers. So there is one keynote address today in the inaugural session. There are 3 plenary and 3 evening lectures, 151 invited talks, including 91 from abroad. The speakers are from abroad. And we have 60 oral presentations and 261 poster presentations by young researchers, PhD students, postdocs, and young scientists. I am sure all of you will be having a fruitful and rewarding talks, discussions in the coming 3 days. So I wish you all the success with this important conference and look forward to learning about the outcome. Thank you very much.
Thank you, sir. Next, I would like to request Professor Bhaskar Mitra, sir, tutorial chair ICEE-2020, to give us overview of the tutorial session for this ICEE-2020.
Hello, everybody. It's great to be here. I think so. Tutorials we had yesterday. I think we had a scintillating tutorial session. We had tutorials on 4 topics: neuromorphic computing, wide bandgap devices, terahertz electronics, and nanophotonics and plasmonics. So there were over 100 participants and distinguished speakers from India and abroad. And again, going with the theme, I think this year tutorial sessions were both very well attended, and we were able to organize very good talks because we were able to get these speakers free. Otherwise, they have to travel to India. But this time, even despite time zone differences, the speakers very kindly agreed to work late night and early mornings to deliver these talks, and I think it was very well appreciated by the community also. Also, a word about the publication. I'm also the publication chair for this conference, so we really have put in a lot of effort to generate a very high quality publication as per highest IEEE standards. So we have several rounds of reviews, and we have about 126 papers which are finally undergoing another thorough IEEE review process. So I think with that,
Thank you, sir. Now I would like to request the chief guest of today's function, Sri Ajay Sawhney, Secretary MIT, who has joined us online to address the delegates. Over to you, sir.
Professor Neeraj Khare, Professor Ram Gopal Rao, Professor Navkant Bhatt, Professor Rajendra Singh, Professor Bhaskar Mitra, Dr. Stuart Parkin, who is joining us from Germany, my colleagues from MIT who are also present in this conference, other eminent scientists, professors, researchers, students, and other attendees. It's a great pleasure for me to be a part of this conference today. The ICEE has made a name for itself, and I think it goes hand in hand with the journey of India in electronics. In electronics in India, we had seen somewhat low point, around 10 years ago. After that, we have again come back. There is a resurgence in electronic manufacturing. There is tremendous activity in research in electronics led by many of the institutions that are participating here today, many of the researchers who are actually participating here today. And we have seen over the past 5 years a growth in electronic manufacturing in India at the compounded annual rate of about 23%. Starting from somewhat limited base, but now it's a huge footprint that we already have in the area of electronics. And one would imagine that when one has grown at 23% year on year for 5 years, it's time to slow down. We don't intend to slow down at all. We have set an ambitious goal for ourselves of being able to grow electronic manufacturing in India at 30% year on year for the next 5 years. This is the current scale of ambition. This is what we are moving towards. And many of our research programs, many of our schemes from the government are basically coming together to move us in this direction. The role of research and especially the program on nanoelectronics and Netra has been extremely important. We were able to get tremendous participation and leadership from the finest institutions in India in this area. Professor Navakant Bhatt has given a wonderful overview of how that had happened. Now this transcends many more institutions, and we have a huge human resource capability, huge competency that has been built up through participation in this program. We intend to continue and strengthen this program, but let me come back to what we are trying to do in electronic manufacturing. We started with a lot of emphasis on consumer products and also on assembly of mobile phones. This year, we have expanded it to create a very large footprint and been able to attract the finest brands across the globe to come in and do their manufacturing here in India, set up their lines of manufacturing in India, not just for Indian market, but also for the globe. We expect this to continue. Alongside that, because now India is getting positioned as a hub of manufacturing for a global market, we are expecting the component manufacturing ecosystem to also start taking shape here in India. And many of our programs are supportive of this activity. Excuse me. Excuse me. Along with this, we are also taking up activity in stimulating the fabless ecosystem. There is a new scheme that is coming in to help research teams as well as entrepreneurs to get into fabless design of many of the electronic components. Apart from this, we have started work again on trying to attract the silicon fab once again in India. Earlier, our efforts in India in this direction have not borne adequate fruit. We have only a limited capacity fab within the public sector currently in the country. And we recognize the need to move forward with a fab within India. But even more, we recognize the importance of what electronic design and fabless design can do for the Indian ecosystem. In this, we are simultaneously moving forward with very aggressive programs in the area of software products, and from a convergence of electronics and software products, we see immense scope in the coming years for electronic devices. And that is precisely the core thematic area for this conference on the emerging electronics. I would give only a sort of a layperson's perspective that with the coming in of 5G, with the coming in of IoT, and a simultaneous reaching maturity in the e-governance systems, in creating national platforms which bring together disparate systems that had taken shape in healthcare, in education, in agriculture and primary sector, we are moving towards an ecosystem where national programs in each of these key domains of activity create tremendous opportunities. We are able to pool up, or we are able to find mechanisms that will lead to convergence, where massive data sets would become available and present opportunities to researchers, startups, and entities from the industry and academia to innovate, to create new solutions, to create new devices that help those solutions, and actually use these to solve real life problems that we face across all of these sectors. This is the core belief that we are pursuing, that in India, today we have, apart from the largest IT companies that provide services, IT services to clients across the globe, we also have the finest multinational companies. Any major technology company today has a very large sized R&D presence in India. This segment is moving towards software products. At the same time, we are successfully moving towards creation of national digital platforms which bring together the IT part and create opportunities for electronics to be used, create a demand for electronics in each and every sector in a huge manner. We have a burgeoning startup ecosystem. Even in this bleak period of the COVID-19, we have seen the emergence of more and more unicorns from India, technology unicorns from India. And the startup ecosystem this time is not remaining confined only to the big cities and metropolises where IT has been present for a long time. Our startup ecosystem, our institutions of excellence, our incubation centers, and our entrepreneurs are now to be seen in many small towns and cities across the country. And that is where the unsolved problems are seen even more starkly. I think it's a wonderful time for India. It's a wonderful time for Indian researchers, academicians, entrepreneurs to take advantage of not just the existing technologies, but also many of the emerging technologies, create new designs, try to solve those problems with whatever it takes. And a base of electronics, a strength in IT, especially in software products, a capability of entrepreneurship, a supportive ecosystem, especially from the premier educational institutions. I think all these give us an amazing opportunity today to address problems, to find solutions to issues that have been eluding us for a long time. Electronics, especially nanoelectronics, especially many of the new elements that are coming in rapidly into electronics, have to play an exceedingly important role as a part of this larger ecosystem. As we move forward, I see tremendous potential for India's emergence in creation of new solutions, new devices, new sets of technology that combine many of the different segments of technologies that are rapidly coming in and becoming a part of our lives. I would like to compliment the organizers of this conference in having seamlessly moved to an online mode. Not just moved to an online mode, but having done that in style, with a significant increase in the number of delegates that are participating here today. When we attempted something like this recently in the area of artificial intelligence, the responsible AI for strengthening the for responsible AI for social empowerment, our conference actually went on to attract almost 80,000 people from across the globe. The online avatar of conferences is something stupendous. We can't even imagine the kind of power, the kind of reach, the kind of versatility that this offers to us. In India, we have also made an effort to create some video conferencing platforms of our own, and we have tremendous amount of activity going on in this. But I would like to once again compliment the organizers of this conference for having moved into an online avatar. In this online avatar, you don't have to set a limit. I think it's possible for us to imagine these conferences in future moving into much, much larger numbers, into much wider participation. And we can see with how much ease people from across the globe are able to participate, investing only the amount of time that they have to actually spend in the conference and saving a lot of the time that used to go in travel. Of course, networking, as was mentioned earlier, is a very important part of any conference. So it'll have to be a mix of physical conferences and online conferences. But once again, my compliments to the organizers. And I hope that many of the discussions that you have in this conference will help us even further strengthen our resolve, our programs, and our competency in actually delivering what we have set as a task for ourselves. Thank you for giving me this opportunity. Thank you, one and all. Thank you.
Your thoughts. Now I would like to request Professor Neeraj Khare sir to give the vote of thanks.
We are very much thankful to you, sir, Ajay Sawhney ji, for accepting our invitation to be the chief guest of this inauguration function and for giving his thought and valuable suggestions. We are also very much thankful to our director, Professor Ram Gopal Rao ji, for guiding us throughout in the organization of this conference, and all the chairs and co-chairs of this conference, invited speakers, and finally to all the delegates of the conference who are attending this virtual conference. So now we'll move to the keynote address, and we made a request to Professor Stuart Parkin to be the keynote address for this conference, and we are very happy that he accepted our invitation. And now I request Professor Ganguly to chair this session.
Good morning, everybody. It's a great privilege and honor of introducing Professor Stuart Parkin, whom I have known for many years now. And I had the good opportunity of meeting him at IBM. So Professor Stuart Parkin, currently the director at the Max Planck Institute of Microstructure Physics in Halle, and also professor at the Institute of Physics of the Martin Luther University at Halle-Wittenberg. He is also the IBM Fellow, which is IBM's highest technical honor, and a consulting professor in the Department of Applied Physics at Stanford. Professor Parkin is very well known for his work on giant magnetoresistance, the GMR effect, for which he shared the 1994 APS James C. McGrody Prize for New Materials, along with Peter Grunberg and Albert Ferd, who went on to get the 2007 Nobel Prize in Physics. It is very important to note that in the Nobel citation, 6 of Stuart's papers are cited. His work on non-volatile magnetic random access memory is phenomenal, and he could show that using a tunnel magnet, he could form an insulator and use what is called the tunneling magnetoresistance, the TMR. He has great expertise from material science to the device, and that's, I think, key to his success. He has 9 patents on spin valve sensors, more than 30 patents in magnetic tunneling junctions, and overall more than 94, I don't know, the number might have increased, but what I have, more than 94 patents in US. Later on, he has worked on magnetic tunneling transistor, and more important, he is known for the racetrack memory, in which it's a current controlled motion of magnetic domain walls in magnetic nanowires. On a personal note, he is a frequent visitor to Bangalore for meetings. I think this winter school also he would have come, I don't know. But every winter school or off and on, we meet him in Bangalore on several meetings. Very interesting personality, always agile and always humming, and great personality. So thank you, Stuart, for agreeing to this request, and I kindly ask you to give your keynote address. So you can talk for around 40-45 minutes and then 5-10 minutes for questions.
Okay, thank you very much. I hope that you can hear me clearly.
Yeah.
It's good?
Yes. Yeah.
Oh, fantastic. Then what I'm going to do is I'm going to share my screen, and then hopefully you will be able to see my foils. So can you see my first foil?
Yes. Yeah, we can see.
Okay, fantastic. Then, first of all, I, of course, would like to thank the organizers for inviting me to give this keynote talk. I'm very pleased and delighted and honored to do so. And as was just mentioned, I have visited India many, many times, and I hope in the future that will be possible again. What I'd like to do in this talk is to briefly discuss spintronic memories, but I want to focus on very recent work where we've been looking at a range of non-collinear spin textures that could potentially form the magnetic bits within racetrack memory. And this is what I'd like to discuss. First of all, I'd like to, as was mentioned, I moved to Germany 3 or 4 years ago and have built up a new department for carrying out research in nanoelectronics and nano devices. These are some of the PhD students and postdocs that I've hired and who've set up a lot of capability in the last 3 or 4 years in my new institute. And in particular, I'd like to thank these PhD students and postdocs in my institute. I'd also like to acknowledge that some of the materials I'm going to discuss, single crystalline materials, were made by Claudia Felser and her group in Dresden. I'd also like to acknowledge Ingrid Mertig and Birger Goebel from the Martin Luther University in Halle for their theoretical support, and also Chirag Garg, who is a former member of my research group in IBM Research. Spintronics is a field of research which is perhaps almost 30 years old, and it ranges from novel materials and phenomena to applications. And to date, there are 2 major applications of spintronics that were just mentioned. One of them is the use of a spintronic device to read information in magnetic hard disk drives. And this is something that I invented. We called it a spin valve, and a spin valve device is based on the physics of spin-dependent transport in magnetic metals and heterostructures, from which is derived giant magnetoresistance. The head, this introduction of the spin valve sensing device, which is a metallic device, but which has a lot of complicated spin-engineered structure that I invented, was introduced by IBM in 1997 and enabled essentially a 10,000-fold increase in the storage capacity of magnetic disk drives. Well, this spin valve sensor, a metallic sensor, lasted for about 10 years and was replaced in 2007 with its successor, tunneling junction device, which is shown here. And a tunneling junction is a simple sandwich of 2 magnetic layers, shown here in red and blue, separated by a very thin insulating layers. And the electrons tunnel across this insulating layer. And depending upon the orientation of the magnetization of the 2 electrodes, the electrons can tunnel very easily to give a high conductance when the moments are parallel, or when they're anti-parallel, then the conductance can be reduced. And we showed that at room temperature, you can achieve changes in conductance of more than 200%, which is 10 times higher than the largest magnetoresistance developed by a spin valve sensing device. So however, the basic structure of the tunneling junction device that is used in magnetic disk drives is very similar to the spin valve device. It's just a replacement of a copper layer with a magnesium oxide layer. Now, the other spintronic technology, which is very interesting, is something called Emra, Magnetic Random Access Memory. And it's something that we actually proposed in 1995. And the concept here is one takes one of these tunneling junctions, these magnetic tunneling junctions, and you place this between wires in a cross-point array, as shown in this cartoon. And you use a transistor for accessing each of these devices. This is a concept that we proposed, and it's only just in the last year that this magnetic random access memory has become a part of a foundry offering from Samsung. So these are 2 important spintronic technologies to date. I wanted just to then briefly show you how these have evolved over the last 25 years. As I mentioned then on the top, you can see the evolution of magnetic disk drives. And I mentioned already that the spin valve device that I introduced was based on novel materials, interface spin-dependent scattering, and in particular the oscillatory interlayer coupling that I discovered, which enabled us to invent or create junctions or spin valve devices that were actually useful in magnetic disk drives. And these were introduced in 1997. The magnetic tunneling junction recording heads replaced those in 2007. But what's of interest today is that the storage capacity of magnetic disk drives, the increase in that capacity is slowing down. So it's very modest. So we need something else to replace magnetic disk drives. But as was mentioned in some of the preceding comments, of course, we live today in a digital world. In this digital world, 70% of the digital data is still stored on magnetic disk drives in the cloud. So provide this spin valve and subsequently magnetic tunneling junction recording routers has played the most important role in our ability to build the digital world of today. So Emra then, we proposed it in 1995. We actually demonstrated that the concept worked just a few years later in 1999. And with the introduction or the discovery of giant tunneling magnetoresistance in magnetic tunneling junctions using magnesium oxide tunnel barriers, we could then build in 2005 a 16 megabit device fully integrated with CMOS, demonstrating its potential. However, it has taken another decade before Emra has become essentially a high-performance foundry offering from Samsung, which was announced last year. So I think this was a major achievement. However, MRAM, although it's a high-performance non-volatile memory, it's unlikely to achieve the densities required, for example, to replace dynamic random access memory. So I want to talk about now a technology, a Spintronic technology that I think has the potential to be both a high-performance, super-fast replacement for SRAM, as well as a super-dense memory that could replace magnetic disk drives. And this is magnetic racetrack memory, something that I proposed actually in 2002. The patents, my basic patents, were issued in 2004, and we demonstrated the fundamental principle a few years later. So the basic idea shown in this cartoon you can see is that you have a magnetic nanowire, the racetrack, which is homogeneous, and in which we can create magnetic domains in red and blue directions, basically up and down, and the information is encoded in the domain walls between the blue and red regions. And the basic fundamental principle that makes racetrack interesting is that when you pass current into these nanowires, you can move all of the domain walls around the wire. So you bring the information to a reading device and to a writing device that is integrated into the racetrack. That is the idea. If we could build these vertical racetracks, we could easily achieve the capacity of a magnetic disk drive in a completely solid-state device without any moving parts. So it would be very reliable, very high performance. It would be 1 million times faster than the magnetic disk drive, and of course use much less energy. We believe that we're on the cusp of achieving such a racetrack memory because of developments in the physics over the past decade, which I want to briefly discuss. And this this figure is from a paper we published in 2015, a small perspective on the evolution of racetrack. And essentially, there have been 4 major developments in the last decade that have brought us to where we are today. I'm not going to discuss each of these developments, but basically, we can now move magnetic domain walls at speeds exceeding 1 kilometer per second. And it enables devices that could operate even at picosecond speeds. So this, I think, is a remarkable achievement. Today, all of the racetrack memory devices we've created are horizontal, shown on the left. The vertical devices are much more difficult to make because of the need to build racetracks on vertical walls. However, we are making progress, for example, using atomic layer deposition and some other chemical vapor deposition techniques. However, even using the horizontal racetracks, you can imagine stacking one racetrack on top of each other, and this leads to very high densities. It's just like vertical flash today. Well, here's some references if you're interested in the details of the physics behind racetrack, but I want to just mention a couple of points. One is that the racetrack devices today involve engineering of atomically thin magnetic layers. On the one hand, we want the magnetization within the racetrack not to be parallel to the racetrack, but to be perpendicular. This enables us to make narrower magnetic domain walls. When we do this by, for example, making ultra-thin layers of cobalt and nickel, each layer is just 1 to 3 angstroms thick. We can make this by conventional sputtering techniques. These form very beautiful, perpendicularly magnetized domains. And at the same time, we build these structures on underlayers that are formed from heavy metals like platinum or tungsten that have very strong spin-orbit coupling. What that does is it leads to first it breaks the symmetry of the cobalt-nickel multilayer, and it forces the domain walls to be chiral. They have a chirality. And this is shown in the cartoon, where you can see a red and a blue plane. And as the magnetization rotates from an up direction to a down direction, it rotates in a plane perpendicular to the domain wall and in a certain chiral direction because of something called the Diluginsky-Maria interaction. And this is an interface exchange wherein if you break time reversal symmetry, this can lead to a vector exchange interaction between the magnetic moments at the interface. This was found many decades ago in a number of different systems. But this is very interesting. Depending on whether we use platinum or tungsten or iridium, we can get a different chirality of the domain walls, but all the domain walls in the racetrack formed in this cobalt-nickel multilayer will have the same chirality if we use an underlayer, let's say of platinum, it will be clockwise. If it's a different material, it can be anti-clockwise. Later on, you'll see why this is very important. Another important physics is the proximity-induced magnetization within these metal underlayers. I don't want to talk about that. Rather, I want to briefly mention another effect, which is key to racetrack, which is something called the spin-Hall effect. So you're all very familiar with the Hall effect. If you apply a current in a metal in a perpendicular magnetic field, then you will cause an imbalance in the electron density, the Hall effect. In the Hall, you see a voltage lateral to the current. Now, the spin-Hall effect is there is no voltage appearing laterally and no accumulation of electronic charge, but rather you get an accumulation of electron spin, as shown in the top right of this figure. On the left side, as you pass current shown in yellow into platinum, you see electron spins appear which are oriented in the red direction, and on the other side of the wire in the blue direction. And it turns out that this is a chiral phenomenon. An electrical current produces an accumulation of spin oriented in a chiral direction, clockwise or anti-clockwise, to that current direction. And so this means on the surface of this layer, we achieve a accumulation of electron spin. And that spin carries angular momentum, and that angular or spin angular momentum now can diffuse into a neighboring magnetic layer, providing a torque on the magnetic moments in that neighboring layer. This is what it looks like. So then here is a cartoon of a chiral domain wall. The magnetization is rotating from up red direction on the left to a down direction on the right. And then underneath, we have a platinum layer in which by passing electrical current will generate spin oriented perpendicular to the current direction. On the top surface shown in red, on the bottom surface of this platinum layer, the spins are oriented in the opposite direction. But the red moments in the surface of this underlying platinum layer can diffuse into this domain wall and cause it to move. And this is the essence of racetrack memory that makes it possible this enables very fast motion of these domain walls when you pass current into this device. And it turns out, again, without going into any details, what makes racetrack really exciting today is this concept of using a synthetic antiferromagnetic racetrack. In Spintronics, a key to developing nanoelectronic devices is controlling the long-range magnetic dipole fields from magnetization. Otherwise, there's interaction between neighboring magnetic bits in magnetic random access memory, for example, or in racetrack, domain walls will interact with one another. You have to eliminate the magnetization. And so a concept that actually I invented 25 years ago, and which was used and is still used today in magnetic recording reed heads, is something I call a synthetic antiferromagnet. And it relies on the oscillatory interlayer coupling through transition metal layers that I discovered in 1989. And in this case, shown in this cartoon, you can see a racetrack which is formed from two racetracks, a lower racetrack and an upper racetrack. They're separated by an ultra-thin layer of ruthenium. It's approximately 7 angstroms thick. And this causes very strong anti-ferromagnetic coupling between all the magnetization in the lower racetrack and the upper racetrack. And by designing these upper and lower racetracks to have the same magnetic moment, this means that in the racetrack, there is no net magnetization and therefore no dipole fields. This means there's no interaction. And it turns out when we invented this just 3 or 4 years ago, we discovered that this coupling, the anti-ferromagnetic coupling through this ruthenium layer, leads to a new type of exchange torque, which is very large and accelerates the domain walls, enabling us to achieve speeds of the domain walls where we pass current through the racetrack of more than 1 kilometer per second. And this is what makes racetrack interesting today. It's key that there's no net magnetization, no dipole fields, and that the domain walls can be moved at these super high speeds. So we believe, or I believe, this makes it possible to build, for example, a static random access memory replacement by using a racetrack, which is extremely short, 100 nanometers or less in length, in which we have a single domain wall moving backwards and forwards, and we can detect it using an integrated magnetic tunnel junction. So we've already demonstrated this in wires that are less than 100 nanometers wide. We believe then, or I believe this could be a very interesting replacement for SRAM, which, as you know, is a huge memory cell. A memory cell using a single domain wall racetrack would be 20 times or smaller. So I think this is a very interesting possibility. Just to show you what this looks like, in this case, we're using magneto-optic microscopy, which is just basically reflecting polarized light from the surface of the racetrack and detecting the change in the polarization of the light. And in the top, you can see 20 domain walls that are moving at speeds of about 300 meters per second as we pass current pulses into the wire. And underneath, you can see the synthetic anti-ferromagnetic racetrack. I hope you can see the motion of the domain walls backwards and forwards, moving at a speed of just over 1 kilometer per second. So in summary, racetrack is super exciting. Over the last 10 years, we've evolved it from just a concept, an idea, to the demonstration that indeed current pulses can move a series of domain walls, all at the same speed in one direction and in the opposite direction when the current direction is reversed. It's caused by spin-orbit torques, which are derived from an interplay of 4 spin-orbit coupling-derived phenomena: perpendicular magnetic anisotropy, proximity-induced magnetization, chiral domain walls due to a Diluginsky exchange interaction, and spin currents derived from spin-Hall effects. And these spin-Hall effects in platinum and tungsten oxide are much larger than people had ever anticipated. They're of the order of 20, 30%, even 40% in some new materials we've recently discovered, making, again, racetrack very, very interesting. This is what I wanted to say about racetrack. What I'd like to do next is briefly discuss our work on other types of non-collinear spin textures, chiral spin textures. This is a very interesting development in the last few years, in fact, in the last 2 or 3 years. And this involves, first, not in thin film structures, but we're going to explore these non-collinear spin textures in single crystals, made, as I said, by Claudio Felser and members of our group at the Max Planck Institute in Dresden. And in particular, I first want to briefly discuss some compounds which are called Oyster compounds. Now, Oyster compounds are a very large family of cubic materials, some of which are magnetic, some of which are non-magnetic. And some of the magnetic Oysters have a distorted structure. They're tetragonal, and the magnetization can be out of plane. There's an out of plane magnetic moment direction from the tetragonal distortion. These are also ferrimagnetic, and not ferro, they're ferrimagnetic systems. So a typical Oyster I'm going to discuss is, for example, manganese 2 platinum tin. And along the tetragonal axis, the structure consists of planes formed from manganese and platinum, alternating with planes formed from manganese and tin. And in each of these planes, the magnetic moments are oriented parallel, but from one plane, manganese platinum, to the next one, manganese tin, the moments are oriented anti-parallel to one another. And it turns out the moments in the two planes are slightly different, so there's net magnetization moment. And what was discovered a few years ago, actually, we showed that these types of systems develop something called a topological effect, which means that there's interesting new scattering mechanism, which is most likely derived from non-collinear orientation of the magnetization. So I want to just briefly then remind you or introduce to you the concept of a skyrmion and an anti-skyrmion. So it turns out then that if you have a material which is magnetized in one direction, let's say along this tetragonal axis, for some region of temperature and magnetic field, the magnetic moments are not oriented parallel to one another, but the ground state breaks up into an array of skyrmions or anti-skyrmions. Now, what is a skyrmion? Then it's basically a circular object in which the magnetization outside is oriented up, and in the middle it's oriented down. And the wall surrounding this object is chiral because of a volumetric Diluginsky rare exchange interaction that wants the moments neither to be parallel, as in a ferromagnet, nor anti-parallel, as in an antiferromagnet, but it wants the moments to be perpendicular to each other in a vector direction, which defines a chirality. And in a block skyrmion, I hope you can see in this cartoon, the magnetization rotates from an up direction to a down direction by rotating parallel to the boundary. Whereas on the right-hand side, you can see a nail skyrmion. This nail skyrmion, the magnetization rotates from an up direction outside this small object to a down direction inside by rotating along the radius of this object. So they're two very different objects. Now it turns out the chiral domain walls that I just discussed for a racetrack have like a nail domain wall structure. But it turns out then the skyrmion was discovered about 10 years ago in a B20 compound, manganese silicon, and these show these block skyrmions on the left. Now it turns out there's another object, an anti-skyrmion, in which has a much more complex structure. So the boundary, as you can see, hopefully in the middle of this foil, the boundary has alternating nail and block components to the wall. So as you go around the circumference of this object, then the wall changes from a nail wall to a block wall, backwards and forwards, and the chirality is also changing. This leads to very interesting transport properties. But we were the first to discover this anti-skyrmion just 3 years ago. And how did we do that? We did it using Lorentz transmission electron microscopy. You basically transmit a very high energy beam of electrons, in our case 300,000 volts, through a very, very thin lamella, which we cut out of a single crystal using focused ion beam milling. And then the electrons, as they pass through this lamella, are deflected by the in-plane components of the magnetization due to the Lorentz force on the electrons. And this causes then an image to be formed that reflects the magnetic moments within these structures. So we can simulate these structures using micromagnetic simulations, and then we can calculate what we expect the pattern in the transmission electron microscope to look like. So this is basically called Lorentz transmission electron microscopy, and you can see these are the patterns shown in the bottom. On the left side, the Bloch skyrmion looks in the microscope like a single dot, a white bright dot where the electrons are focused. On the right-hand side, the nail skyrmion, you actually see nothing in the microscope if the electron beam is transmitted perpendicular to the plane of the skyrmion. And in the middle, you can see the anti-skyrmion. Because of this complex domain wall structure, it forms this cloverleaf pattern where you see increased intensity, these two white regions vertically, and horizontally these black regions of decreased electron intensity. So it has a very characteristic pattern. And this pattern is what we saw in a Oyster compound for the first time, an anti-skyrmion. And so if you look here in A, you can see this cloverleaf structure, which again is the image we see in a Lorentz transmission electron microscope mode. We see this cloverleaf pattern in this Oyster, which is a manganese platinum tin based compound. And we published this in Nature 3 years ago. Now it turns out that we can see these individual anti-skyrmions, but typically they form an array. So if you look in part C, you can see here an hexagonal array of these anti-skyrmions. And it turns out then that the rest of this image shows you that these anti-skyrmions form arrays depending upon the temperature and the vertical magnetic field. As we increase the outer plane magnetic field, eventually they will disappear as all the magnetization in the structure is oriented parallel to one another. Okay, so now I want to talk about another very interesting aspect of these anti-skyrmions is what happens when we change the thickness of the lamella through which we are directing this electron beam. And I want to show you then, first of all, if you look in the middle, you can see this is a scanning electron micrograph of a lamella, which is a wedge-shaped lamella we formed by focused ion beam milling. And on the left side, you can see the Lorentz transmission electron micrograph in zero magnetic field. When it doesn't form anti-skyrmions, it turns out that the structure forms instead a helical structure, and the helices are oriented along two crystal directions which favor Bloch domain walls in this anti-skyrmion structure. And so in the left, you can see these black and white lines. These correspond to magnetization pointing to the right and to the left in the plane of this material as the magnetization undergoes a helical variation along a given direction with a given period, and the period of this helix is determined by the ratio of the Diluginsky-Maria vector exchange to the Heisenberg exchange that favors parallel orientation of the magnetization. And then if you look here in the bottom, we've highlighted three regions within this micrograph A, B, and C with three different thicknesses. And in the bottom, you can see a series of micrographs starting from large outer plane magnetic field, 0.27 Tesla, where in A, B, and C, basically mostly the anti-skyrmions are not observed. There's a uniform magnetization. And as the field is successively reduced from the left to the right, you can see at intermediate fields, you can see the arrays of anti-skyrmions, and eventually in small magnetic fields, you see these beautiful black and white stripes like a zebra which correspond to a helical rotation of the magnetization oriented along two different directions. So what is interesting is that the stability of the antiskyrmions is much greater than that of block skyrmions observed in the B20 compounds, which have been extensively studied. The antiskyrmions appear over a very wide range of magnetic field and temperature, almost up to the Curie temperature, and they can be stabilized even in zero magnetic field. Now, what we discovered was, from this Lorentz microscopy, we could look at how the period of these helical structures, again, these are shown here, changes as we increase the thickness. And you can even see in this Lorentz micrograph on the right-hand side by these yellow lines, as we increase the thickness of this lamella, you can easily see that on the right-hand side, the period of between the white lines, white and black lines, is much smaller than on the left side in the thicker region. And it turns out that the period shown on the left of this helix is increasing by more than a factor of 2 as we increase the thickness of this lamella from 40 nanometers to 180 nanometers. This was quite a surprise because to date, in no other system had such a strong variation of the size of the helix, and I'm going to show you in the next foil of the antiskyrmion varied in this dramatic way. Now it turns out that we wanted to look at thicker lamella, so thick that the electron beam cannot be transmitted, so we switched then to magnetic force microscopy, which detects the outer plane component of the magnetization. And on the left, you can see a very beautiful magnetic force microscopy image showing the outer plane component of the magnetization. And you can see in the line profile that it varies in a sinusoidal fashion consistent with a helical propagation of the magnetization. In the period, you can see is 300 nanometers here. And on the right-hand side, you can see that the period of this helix is increasing from 100 nanometers when the lamella is 50 nanometers thick to 600 nanometers when the lamella is 1.6 microns thick. And we see basically a monotonic increase of this helical wavelength over this entire thickness range. We can extend that range further and up to 4 microns, and then we can see that the helical period has increased to more than microns. So we can easily observe this using optical microscopy. We don't need to detect these helices using magnetic microscopies. And on the left, you can see a series of images in which, by applying in-plane magnetic fields, we can reorient this helical domains from one direction to another direction, to a direction in B, which is perpendicular to the lamella, and in C and D, which is along the length of this lamella. And we can see this beautiful sinusoidal variation of the outer plane component of the magnetization consistent with a helical structure. So it's amazing. So the magnetic force microscopy and the Lorentz TM agree with one another. And then finally, by varying the magnetic field in the magnetic force microscope, we see now these individual circular objects, and these are antiskyrmions. And I think you can easily see in this structure, in the image ABCD, on the left, the structure is 100 nanometers thick. On the right, it's 4 microns thick. And I think you can readily see that the size of these circular objects changes from small on the left to big on the right. And on the right-hand side, you can see a plot that the diameter of the antiskyrmion increases from 100 nanometers when it's thin to more than 1 micron when it's 4 microns thick. And the size of the antiskyrmion exactly matches the period of the helix because both are derived from the same physics, the ratio of the Diluginsky-Maria exchange related to this broken time reversal symmetry tetragonal Oyster structure to the Heisenberg exchange. And then I just wanted to mention that it turns out that there's a complex zoology of these non-collinear objects, spin textures. And it turns out in the same Oyster compound, we've discovered we can actually form block skyrmions, but they're elliptical in shape, unlike the B20 compounds. And we can stabilize in these beautiful superlattices of elliptical block skyrmions in these materials. And without going into any details, it turns out that the reason for the formation of these elliptical block skyrmions and the reason for the variation in size of the antiskyrmions and the helix period with thickness is derived from long-range dipole coupling. And it's a property of the very low symmetry of the crystal structure of these Oyster compounds as compared to the cubic B20 materials that have been so heavily explored. So this is a very interesting and unusual property of the Oyster compounds. But just I wanted to finally mention there is another compound which we've recently discovered in which we can see a closely related property. It's a totally different structure. It's a layered structure, platinum, manganese, gallium. It has a perpendicular magnetization. And we discovered that the structure in the literature is wrong. It's broken. It has it's not a centrosymmetric structure, and therefore it actually has a very interesting layered structure consisting of platinum, manganese, and gallium successively, basically a layer of manganese moments, which is magnetic, separated by a layer of platinum gallium, but the platinum gallium layers are rumpled. So we actually have a very beautiful structure, platinum gallium manganese, and this gives rise to this Diluginsky exchange because of this broken symmetry. And in this structure, we've discovered, again, for the first time in a metallic compound, a nail skyrmion. As I mentioned earlier, in the Lorentz micrograph, we cannot see these structures when the beam is exactly perpendicular to the lamella in which we observe them. We have to tilt the sample, and then we can observe. I think you can see very faintly in this structure these nail-like skyrmions, and this shows you the same material observed by magnetic force microscopy, and then we can see beautifully the outer plane component. And as we vary the thickness in this lamella from the left to the right, we find that the size of these nail skyrmions changes dramatically, as you can see from the size of these red blobs. And the size increases again from 100 to more than 600 nanometers as the thickness of the lamella is increased to 3 microns. So we've demonstrated the possibility of tuning the size of these objects by tuning dipole fields, which is very interesting technologically. Now, finally, I have a few moments left, I think, and I just wanted to mention that in my institute in Halle, we built this system over the last 3 or 4 years, in which we have a 15-meter long ultra-high vacuum tube, which is shown in this picture here. And this tube connects several different deposition systems, including something here we call Mango, which is a system we've designed ourselves, completely automated. We want to accelerate our ability to discover new materials. We have 40 different sources for magnetron and ion beam sputtering behind gate valves. So we could really make an exotic range of materials. But these sputtering systems are connected to a system here shown in the top left, which is 2 molecular beam epitaxy chambers, one designed for oxide, one for nitrides. And these systems also are connected to this ultra-high vacuum tube. So we can build on the same substrate using molecular beam epitaxy, using magnetron or ion beam sputtering. And also we have a pulsed laser deposition, which is not shown in this photograph, but which is now installed in the laboratory. And all of these systems are connected also to a photoemission system for looking at electronic structure in situ. And we've also connected it to a dry box where we can exfoliate materials. So we have a very, very complex, I think one of the world's most sophisticated systems for building thin film structures from various thin film deposition techniques, molecular beam epitaxy, pulsed laser deposition, and exfoliation. And this is what is shown here in this view point. So any of you who might be interested in, for example, doing a PhD or a postdoc or visiting to carry out research, please come and visit and take advantage of this, I think, unique system for exploring and engineering thin film structures for applications in nanoelectronics and beyond. Now, if there is a few more moments, I wanted to briefly mention that in the last 3 or 4 minutes, one other aspect of the work we're doing, which is a very interesting concept of using ionic liquid gating to create spin textures using the very large electric fields that ionic liquid gating develops. So you're all familiar with a field effect transistor shown on the left. You have a gate insulator across which you apply voltage to develop electric fields that introduce charge into a channel. On the right-hand side, you can see we replace the conventional dielectric, let's say hafnium oxide, we replace it with an ionic liquid consisting of large organic molecules, half positively charged, half negatively charged. You apply a gate voltage and you cause an accumulation of charged molecules of one type at the surface of a channel. Shown here, positively charged molecules at an oxide surface. And we discovered a few years ago that these electric fields are so great that they cause oxygen to leave the oxide. And this can cause dramatic changes in properties. One of the ones we looked at was vanadium dioxide, which is an archetypical Mott insulator, which shows it's metallic above 300 degrees and becomes an insulator at low temperatures through a metal to insulator transition. And we showed by ionic liquid gating, we could completely suppress the insulating state shown on the left. The purple curve that shows fantastic insulator, the red curve shows after this ionic liquid gating, if it remains metallic to low temperatures. And we showed in a paper we published in Science in 2013 and in all these subsequent papers, this is due to the removal of oxygen from the vanadium dioxide film. And that removal happens over up to 1 micron from that surface interface with the ionic liquid. Let me just hurry on. Recently, we and others have shown that in strontium cobalt 03, we can convert a perovskite, a metallic ferromagnet, shown on the right, we can convert that to an insulating antiferromagnet, strontium cobalt oxygen 2.5, using liquid gating, and it causes, again, removal of half a mole of oxygen, and you can switch from one to the other by changing the field or the voltage across that electric double layer. So we can switch between a metallic ferromagnet and an anti-ferromagnetic insulator. And what we've shown is, we published this 2 years ago in Nature Communications. On the left-hand side, you see a high-resolution transmission electron micrograph of a brown millerite. And I think you hopefully can see the unit cell is doubled because the oxygen removal. But as we start to liquid gate the system, you can see in B from the surface, it's converted to the perovskite. And then as you wait, takes a few minutes, we can convert the structure here, which is 100 nanometers thick, from the brown millerite to the perovskite. And this is reflected in the fast Fourier transforms at the bottom. The larger unit cell, in the case of the millerite, is converted to a smaller unit cell of the cubic system, the perovskite, during gating. And we can go, in this case, we're injecting ions, oxygen ions, into strontium cobalt 02.5 to go to the strontium cobalt 03. If we reverse the voltage, then we can go backwards and basically remove oxygen. So we can do both things. Why am I telling all this? Because we want to use this idea to create spin textures. Just another point, turns out that if we start with the, on the left-hand side, shown in B, this is the perovskite, it's cubic. Now, depending upon this gating voltage, we've discovered we can make a brown millerite with the vertical orientation of the layers in which the oxygen is removed, or they can be horizontal, depending upon the gating voltage, low or high. Liquid gating causes removal of oxygen vertically or horizontally. Why I'm telling you this is because we want to use this to create spin textures. So what we do, we take a film of strontium cobalt oxide, we put a resist on top, and we make holes in the resist, shown in these black holes, and then we gate through the holes. And this just shows you that if we take a strontium cobalt oxygen 2.5, which is insulating, we see no current in a conducting atomic force microscope. If we cover it with resist and then gate, nothing happens. And if we cover no resist and gate, becomes green, very, very conducting as we switch from the insulator to the ferromagnetic metal. And so now we do this by looking through holes. These are micron-sized holes in a resist layer. And after we remove the resist, we carry out the conducting atomic force microscopy. We can see on vanadium dioxide, the region in the hole in the resist layer on top of the vanadium dioxide is converted to a metal. And we see conductivity. The same applies for lanthanum, strontium manganese oxide, and strontium cobalt 2.5. And it turns out then, and without going into any details, running out of time, we can now form very complex spin textures shown on the left in this checkerboard image. This checkerboard image is the conducting atomic force microscope image of a film of strontium cobalt oxide, which we've converted the purple regions to a form of the brown millerite, where the oxygen vacancy layers are horizontal and neighboring are vertical. And you can see the boundary between these regions is just 5 nanometers wide. And underneath, you can see this again, transmission electron microscopy image, conventional imaging mode, where we can go from a parallel to vertical orientation of these regions on a scale of approximately 100 nanometers. And on the right-hand side, we've created structures formed from ferromagnetic metal, the shown in green, and the blue is the insulating antiferromagnet. So we can create actually a whole series of novel spin textures in this way, down to a scale of about, we believe, down to 10 nanometers in size. So I want to summarize by saying spintronic memories have two major applications already. One, spin valve sensors, tunnel junction sensors for reading tiny magnetic field and magnetic disk drives, enabled a 10,000-fold increase in the capacity of magnetic disk drives, and that is where all the digital data today is stored. Magnetic random access memory promises a new type of high-performance, non-volatile random access memory, just emerging into the marketplace as we speak. Magnetic racetrack memory, the physics and the materials we've developed over the last 10 years mean that we're on the cusp of building racetrack memories that could, I think, make their way into the marketplace within a few years. We can move the domain walls where we store information in racetracks at speeds of more than 1 kilometer per second in synthetic antiferromagnet racetracks. And in part of my talk, I also discussed the very interesting recent developments in spintronics that suggest that non-collinear chiral magnetic nanoscale objects will potentially could be used in racetracks in the next few years. And I also wanted to mention whether novel ways of creating new types of magnetic spin textures using liquid gating and local removal of oxygen. And I want to thank all my collaborators here. So I'd like to thank you very much for your attention and appreciate very much having the opportunity to talk to you today.
So actually, we are running out of time because 11 o'clock, the other parallel sessions will start. But okay, if there is a quick question, you can put through your chat box or ask option. There's a ask question option in the delegate virtual hall. So if there is a quick question, then please, we can ask Stuart one question before we wrap up. So Stuart, great work. I just wanted to know that regarding this new thing that you showed, this ionic liquid stuff, is it right now only on strontium cobaltate, or you have tried other brown millerite structures like calcium iron oxide?
So far, that's the only brown millerite that we've explored, but there are, of course, as you said, There are quite a variety of ground minerals, and I think they're very interesting to explore, in particular, how we could use liquid gating to create different structures, let's say, depending on the voltage, something we don't fully understand, but that I think is a very interesting possibility.
Okay. Any other question? You want to ask?
Yeah, Stuart, I have one question. There are many ways of memories are evolving through course of time. So, what is the perspective? How in future things will go and emerge? Can you make some comment on that?
You mean, let's say, racetrack compared to other?
Yeah, there is different memories, and also we start talking of the ferroelectric memories and all that. So, how in future they are going to come up in future?
Well, I think, quite frankly, racetrack memory is superior to all these other possibilities. So, ferroelectric memory has major problems in terms of switching many times, and you lose information. I think that's a major problem. Cannot be made super small. Racetrack memory, what makes it unique is that it's a shift register. You have the ability to store information at densities even greater than the lithography node, because it's based on these spin textures. The carbon in the wall could be an antiskirmion, a skirmion, which can be very tiny. So I think it has, it's totally different and has much more possibilities than any other memory today. And also, quite frankly, we could use racetrack memory also for neuromorphic computing, as I think there are very interesting potential possibilities there too. And I would say, let's say the other resisted memories have problems because you have to change the state of the material. And basically any memory in which you start to move atoms, like ferroelectric, like resistive memories, usually have problems of survivability, of switch, how many times you can switch. Electric memory, nothing happens. We just change the spin texture without moving any atoms. And it's a totally reliable memory. I think for all these reasons, and the fact that it can be super fast, that the waveforms can be super small, and then we basically demonstrated this all works. I think it has, it's one of the most interesting emerging memories, which will have enormous applicability in the next short period of time.
So I'm sure everybody would have seen how wonderful Stuart has shown from basic physics to materials to the latest devices and the vision to the future in memories. We all thank Stuart for kindly accepting the invitation, and also I am very honored that the committee asked me to chair this session. Thank you very much, Stuart. So I hand over to the committee.
Okay, thank you very much, Professor Stuart, for this very nice talk and illuminating things and accepting our invitation for this one. And we are really very honored. I'm also thankful to Professor Ganguly for chairing this session. Now this session will finish, and now the 8th parallel session will start on a different subtopics. Okay, sir. Thank you very much.
Thank you.
Thank you, sir.
Thank you.
Bye-bye.
Thank you very much. Bye-bye.
Bye.
Bye. Bye.
Okay, cheerio. Bye-bye.